So far, all the graphs we've done have been for objects with constant velocity. And another way of saying that would be uniform motion. Velocity is constant during a time interval. So now let's do ones that are not uniform motion. For this graph, I have sketched out a position versus time graph, and in this case I listed it as position as x, meaning maybe left and right. So maybe I can imagine an object starting left of my origin by 1 meter, and then it went rightward and got to the origin, x equals 0, and then it moved more to the right, 3 meters to the right. And then I could turn around and come backwards and move left again to move back to the origin, and then keeps going left of the origin to go back to its starting point. So if I look at this, I see here that it looks like there's a small kind of instantaneous, at that instant, flat region right here. So it would be stopped for an instant. Same here and here. So we could say that the instantaneous velocity, or the velocity at that instant, is 0. And that's because the slope of the position versus time graph right at that point is 0. Here, it looks like it might have had the maximum positive slope, so that would be its maximum positive speed towards the right. And here could be the maximum negative speed, so its maximum speed to the left. Here's an intermediate speed, kind of while it's speeding up. And then it's going to slow down a bit. So let me sketch in a few kind of intermediate points to look at. So it looks like it was at rest. It's got some speed to the right because it's got a positive slope. Now it's a steeper positive slope, so it's faster to the right. It shallows out again, so it's going to slow down and stop. Now it's going to have some speed, but in the negative direction to the left. Right? It still has speed to the left. Looks like it's shallowing out here, so it's going to slow down and then stop. So how about we try to graph that out roughly on a velocity versus time graph? So velocity in the x direction in meters per second. So it had 0 velocity at time of 0 because the graph was flat. At 0 velocity at time of 2 because the graph was flat for an instant. And again at 4. Now it looked like it had maximum positive velocity at around time of 1. So I'll put a dot here. And it had weaker positive velocity at roughly time of a half. So I can put a dot here. And same thing at maybe time 1.5. It had a positive slope, but not as steep as this one. Here, I had a negative slope, and it was kind of a mirror image of this. So instead of being positive at a certain value, I'm going to go negative at that same value. At time 2.5, It had a negative slope, but maybe not as steep as this one. So at this time frame, it had a negative slope, but not as steep as this one. So maybe I'll draw a dot in here. So if I connect the dots, we end up with a velocity versus time graph for that object, for that motion. Here's going to be faster in positive direction. Here was stopped. And this was faster in the negative direction. So these two graphs represent the exact same object doing the exact same thing, just looking at it in completely different ways. And you can see even if we were to look at this time frame of 1 second, the velocity is not constant. It changes smoothly from 0 to a positive maximum value. At no point here is the velocity constant, a flat line. Like before, we could use the area under the graph to try to figure out a displacement for the object. So let me estimate, maybe this was a value of 4 and negative 4. So we just keep going with our example. So what about this time interval from 1 to 2 seconds? What is the area under the graph here from 1 to 2 seconds? So we could find its displacement during that time. Looks to me like a triangle. And the area of a triangle is 1/2 base times height. The base of the triangle here is 2 seconds. And the height of the triangle from the axis to the peak would be 4. And it's not just 4, it's 4 with units, 4 meters per second. So then the seconds could cancel out and the 2's could even cancel out, so we end up with 4 meters. So looking back at the graph from 0 to 2 seconds, does it look like we gained 4 meters? We went from -1 to +3. For this time interval from 2 to 4 seconds, I see a triangle, but it's in the negative velocity region. It's under the axis. So I need to make sure that I'm going to end up with a negative area. I'm going to do that by doing 1/2 base times height. The base of that triangle is 2 seconds long. And for the height, I'm going to say from the axis, it goes to -4. So for the height, I want to put in -4 meters per second. The seconds can cancel out, the 2's can cancel out, so I end up with -4 meters. So I do end up with a negative value here, which I wanted. And then if we go and look at the position graph up here, does it look like from 2 to 4 seconds that we lost 4 meters? We went from +3 and ended up at -1. So we did lose 4 meters. Now we'll deal with acceleration, which is one of the key topics for the class. And acceleration is going to be the rate of change of our velocity. So the equation of this is going to be acceleration. It's going to be equal to the change in velocity over the time interval, or the change in time. Abbreviated, we could say the acceleration, and usually we'll specify in the x direction or in the y direction. So let's just imagine the x direction right here. Acceleration in the x direction is equal to the change in the velocity in the x direction divided by the time interval. And then if you wanted to actually figure out this delta v, that would be the final amount minus the initial amount. So Vx final minus Vx initial over the time interval, and that's the final time minus the initial time. So how about I find the acceleration, but let's only focus on the interval from 1 second to 3 seconds, just on this straight part right here. Let's find the acceleration during that time frame. So I'll write out my equation like this. Ax is going to be equal to the velocity x, and I'll say at 3 seconds, because that's going to be my final time, minus the velocity of x, and then I'll put a little 1 here at 1 second. And those subscripts are my choice. They're my note to myself. If you wanted to keep the f and the I, that's fine. Minus my stopwatch reading at 3 seconds, minus my stopwatch reading at 1 second. So my velocity at time 3 was -4 meters per second, minus my velocity at 1 second, and that was +4, divided by 3 seconds minus 1 second. So we're going to end up with -4 minus 4, so -8 meters per second divided by 2 seconds. So then I would end up with -4 meters per second. But I can rearrange this fraction of units to be a meters per second times 1/second, which makes it easier to see why we say the units of acceleration are going to be meters per second squared, because there's 2 seconds in the denominator. So -4 meters per second squared. So what this means is that every second, your velocity will change by -4 meters per second. And hopefully we can see that on the graph. In 1 second, our velocity changed by -4. It went from 4 to 0. In another second, our velocity changed by -4. It went from 0 to -4. And just like velocity, where a negative velocity would mean a leftward velocity, a negative acceleration means a leftwards acceleration. And a lot of people find the sign of the acceleration confusing, so let me teach you the easiest way that I have found to describe it. If the velocity and the acceleration have the same sign, then the object is speeding up. So if an object had a velocity of, say, 1 meter per second, and that's going to be implied to be positive, and it also had an acceleration of 1 meter per second squared, these values are both positive, so it will be speeding up. And it's going to be speeding up in the positive direction. Another example could be if the object was moving left, so we'd say its velocity might be -1 meters per second. And what if it also had an acceleration to the negative, to the left, like something was pushing on it leftwards while it was moving left? So the signs here agree, they're both negative. So it's going to be speeding up while moving in the negative direction. And then opposite of this, if the signs disagree, then the object is slowing down. I have just resketched the velocity graph that we were using, and before we had looked at the area under the graph to the axis, and that would give us the displacement during that time frame. But now let's look at it a different way. The slope of the velocity graph is the acceleration. So during this segment here, from 0 to 1, the slope would be equal to rise over run. The rise was 4 meters per second divided by the run of 1 second. So we end up with 4 meters per second squared. During this whole time, from 1 to 3, it had the same slope, and let's find that. Its rise was actually a fall, so it fell -8 meters per second. And the run was 2 seconds. So -4 meters per second squared. We found that earlier using the equation. We find it again this way by looking at the graph. And here, the slope is the rise, so from -4 to 0. So that was a rise of +4 meters per second, and that took 1 second. So 4 meters per second squared. So let's highlight the regions here where it's speeding up in green. And we can figure that out by looking for positive velocities with positive accelerations. So during this segment, it's a positive velocity and a positive acceleration. So I'm going to color this green, meaning speeding up. So now let's look for negative velocities with negative accelerations. So negative velocities with negative accelerations. So this segment here is also speeding up, but it's speeding up leftwards, whereas this one was speeding up rightwards. I'll start a little legend here. And then let's find the times where it was slowing down. It was slowing down. One way we can see that it was slowing down is if the velocity is getting closer to the axis, but we can also see it by looking for positive velocities with negative accelerations. So here it is slowing down. Kind of shade that in with red. And here, a negative velocity with a positive acceleration. That's also slowing down. We can also see it again by the velocity with time is getting smaller, going back towards the axis.